Let's explore what happens when a linear program has no finite solution due to unboundedness. In an unbounded linear program, the feasible region extends infinitely in some direction, allowing the objective function to decrease without limit. Let's understand the conditions that lead to an unbounded problem. During the simplex method, we need to determine if the entering variable can be increased indefinitely. When the coefficient a hat it is positive, the basic variable xbi decreases as the entering variable increases. However, if all coefficients a hat it are less than or equal to 0, then no basic variables decrease, and the entering variable can increase without bound. Let's examine a specific example of an unbounded linear program. Consider this linear program. Minimize z equals negative x1 minus 2 by 2. Subject to the constraint, negative x1 plus x2 is less than or equal to 2. And negative 2 by 1 plus x2 is less than or equal to 1. With non-negativity constraints, x1 and x2 greater than or equal to 0. After 2 iterations of the simplex method, we reach a critical point. The basis contains x1 and x2, while the non-basic variables are x3 and x4. The basis matrix B has these coefficients, and its inverse B inverse is this matrix. The current basic feasible solution has x1 equals 1 and x2 equals 3. Now we check the reduced cost to find the entering variable. The reduced costs for non-basic variables are 5 and negative 3. Since the second reduced cost is negative 3, variable x4 should enter the basis to improve the objective. The entering column for x4 is negative 1. Negative 1. Since all entries in the entering column are negative, there are no candidates for the ratio test. This means x4 can be increased without limit, and the problem is unbounded. Let's visualize the feasible region to understand unboundedness geometrically. The graph shows the feasible region with constraint lines. The current basic feasible solution is at x1 equals 1, x2 equals 3, and the arrow shows the direction of unboundedness. Let's characterize the direction along which the problem is unbounded. From the simplex tableau, we have xb equals b hat minus a hat 4 times x4. All feasible points can be written as this vector plus x 4 times this direction vector. The vector d equals 1, 1, 0, 1 transpose is the direction of unboundedness. This direction satisfies d is non-negative, and a times d equals 0. Most importantly, c transpose d is negative, meaning the objective decreases along this direction. We could have detected unboundedness even at the first iteration. If we had chosen x1 as the entering variable at the first iteration instead of x2, the entering column would be negative 1, negative 2. Again, all entries are negative, which would immediately indicate unboundedness. At the first iteration, feasible points would follow this form with direction vector 1, 0, 1, 2. Let's summarize the key points about unbounded linear programs. Unboundedness occurs when the entering variable can be increased without any limit. This is detected when all entries in the entering column are non-positive. This implies the objective function can decrease indefinitely with no finite minimum. The problem has a direction of unboundedness along which the objective decreases.